Hi there. So we were implementing speech emotion recognizer using support vector machine and MFCC. So basically the goal of our project was to create the recognizer using the support vector machine created from the scratch without using any additional libraries, which allows us to insert sample of our voice and to obtain the correct label of it. So about the dataset. So we use the dataset with the existing recorded messages from different people, men and women. So basically, the dataset consists of several emotions, but we focus on the main three: anger, happiness, and sadness. So about how we actually process our samples, it is called MEL frequency stepstream. So first of all, we obtain the samples, so in the form of waveform, and after that we calculate the power spectrum, which basically we need for identifying the frequencies on the present frames. Before that, we divide it into separate frames. So after that, we use MEL filter banks, which basically tells us how much energy in different frequency regions we have. After that, we scale it to the logarithmic amplitude spectrum. Why we do this? That's because of our perception, because we could not like comprehend it in the linear form. After that, we obtain the 40 vectors, which basically means how much energy in it in each filter bank contain. After that, we take discrete cosine transform, which we basically need because we need to decorrelate the energies of the filter banks. And that's basically our MFCC, but additionally, we find differential acceleration coefficients just to upgrade and improve our accuracy of that. In our specific case, that was 8%. So I just want to quickly look on the code. Like the main function in the class MFCC is logically MFCC. As I mentioned before, first of all, we find the power spectrum that's from our sample. And to do this, we just find the short time Fourier transform and take the magnitude of it just by taking absolute values and calculate power spectrum by the taking to the power of 2 and divide by FT size. After that, we find the filter banks, which basically is done in the in this function. So we take the upper MEL and lower MEL, which basically will be 0, and we found the MEL points to transform to the MEL scale. We just have like these formulas and convert it backwards to the frequency. So what we do here next, just find the filter banks by the formula. And after that, we get the values here, which is basically here in this function. So after we get our filter banks, we need to also consider the machine epsilon, which basically upper bound on the relative approximation error due to the floating point. And after that, we consider it, and we multiply our filter banks by power spectrum and transform it to the logarithmic form. So here we take discrete cosine transform to decorrelate the energies, and this is our substral coefficients here. We consider only 13, the first 13 of them, since the other one just decrease the performance of the model. And after that, we found the differential coefficients and acceleration coefficients, and we found the energy difference, and energy acceleration, and just put it in just in the one array. So that's how we obtained the coefficients here. And after that, we want to discuss about the SVM.
Hello, everyone. So, what is SVM and how it works? SVM is a special tool that allows us to classify different sets of data. So, for instance, if we have two set of samples of data, like here, for example, green points and blue points that possess some X and Y features. So we could plot it on the 2D graph. Yeah, here. Our goal is to find such a hyperplane that would divide our space, this 2D graph, into two subgraphs with a green and blue points, and we also want our margin to be maximum. So margin is this thing. Margin is the distance between our hyperplane and the point. Just right here. Yeah. Why is it called support vector? Because support vectors help us to find this hyperplane. So here are support vector here and here. Yeah, there are also different types of these support vector machines. We could implement support vector machine with hard margin, with soft margin. For example, soft margin allows us to take some misclassifications and just ignore them, while hard margin does not have such an opportunity, but we will discuss it like not today. Yeah, let's move to like the most general question, how we find this hyperplane, how we came to this optimization. And the algorithm to do it is called sequential minimal optimization. And I'll better show you in the code how it works. Here is it. So at first, it would be like a general overview of the algorithm. I will not go into deep details because just inefficiently, I suppose. So suppose we have some set of alphas that allow us to find our hyperplane. We need to adjust these alphas to have the best margin and the best hyperplane that would not misclassify our data sets and will classify correctly all the others, so we could distinguish between different classes. In our case, it's emotions. So first of all, our input is just this vector of 0 alphas. So each alpha is set to 0 at the beginning. Let's move to our main function. It should be here. So yeah, here it is. Our main function. Our main function corresponds to corresponds just to take the right alpha. Just choose the first one alpha. As we have chosen the first alpha, we move to the second step. So basically, this algorithm could be divided into 3 steps. The first step is to choose the first alpha. The second step is to choose the second alpha that would be the most efficient for the first alpha, because we calculate our first alpha depending on the alpha second. So it's just kind of, we are solving our Lagrange function for 2 Lagrange multipliers, so alpha 1 and alpha 2. And then we just optimize our hyperplane using alpha 1, alpha 2, along with calculation of errors, keeping them in cache, and so on. So as we chose our first alpha here, we move to our function examine example. Examine example corresponds to the function that allows us to find the best choice for alpha 2. So first of all, in this algorithm, we are focusing on just 2 alphas. We are taking 2 alphas and optimizing the hyperplane accordingly to them. So we're not just taking all the alphas and just trying to do something. So choosing the best alpha could reduce the time and the energy we need to put in the program overall. So here in examine example, we are choosing the second alpha with respect to our first alpha, and this function requires, this function takes some, uses the help of another function, which is called take step. Take step is created to find the biggest step for alpha 2. So like we are looking, we not just want to go through all the alphas, we need to take the best possible alpha on each step of optimization. So as we chose our second alpha, we are moving to a function take step. Here it is, take step. And here we are calculating relations between alpha 1 and alpha 2, considering with respect to constraints. The constraints are given like by default. One of them are KKT constraints, but it's not like very important to know right now. So we are just choosing the first alpha which violates one of the constraints, and then moving to alpha 2. Then we are calculating, this function actually optimizes two alphas, so alpha 1 and alpha 2, and then we are receiving our alpha 1 and alpha 2. We reload in cache right here, updating cache. Now we're updating cache right here. Yeah, we are calculating the B, the bias, and that's repeating these steps over and over again. We are receiving the vector of alphas that we use to calculate our hyperplane and then to predict the output. So we will show you how it works right now. We will record an audio. Let's move to test here. Yeah, so we have record here. I'll record some 3-second or 4-second message, and then we'll see to which emotion it corresponds. By the way, we have only like 3 emotions here available as for now. It's anger, happiness, and sadness. So let's move to it. So now we'll show you how our SVM works, how it recognizes different emotions like happiness, sadness, and anger. Actually, we have an efficiency of 62% with our custom SMO algorithm, with our custom solver and custom MFCC. So let me record a short message for you, and we will see how it works out. I'm so excited. Yeah, sure. I'm happy. So you could try it on your own. You could try it yourself. We'll leave the code for you. If you want more emotions, let us know in the comments. So thank you. Goodbye.